will see in detail about the stationary perturbation theory, that is time-independent perturbation, particularly the first-order perturbation for non-degenerate case. The eigenvalue equation H get psi is equal to E get psi. H is a Hamiltonian and E is the eigenvalue. The Hamiltonian can be separated into two parts. One is unperturbed Hamiltonian H naught. The other one is perturbed Hamiltonian H prime with the scaling factor lambda. The parameter lambda is important as the assumption that H prime is small suggests that we expand the perturbed eigenfunction and eigenvalue as power series in H prime. This is most conveniently accomplished in terms of the parameter lambda. This lambda varies from 0 to 1. Generally, it is very much less than 1. If lambda is 0 means no perturbation, lambda is 1 means the maximum perturbation, and the perturbed wave function and the energy levels are written as psi equal to psi naught plus lambda psi 1 plus lambda squared psi 2 plus lambda q psi 3, and it will go on. Where psi naught is the unperturbed wave function, and this is psi 1 is the wave function under perturbation condition, that is at energy state 1, this is at energy state 2, like that. Similarly, the energy level can be written as E naught plus lambda E1 plus lambda squared E2 plus lambda Q E3. Uh, E1 is the first order energy correction, E2 is the second order energy correction, E3 is third order energy correction, and it will go on. And now, if you substitute this in the wave equation, H psi is equal to E psi, where, as I said, H is equal to H naught plus lambda H prime psi, which is equal to E psi. Here, you replace psi with this, that is psi naught plus lambda psi 1 plus lambda psi 2 plus lambda squared psi 2 plus lambda cube psi 3. Similarly, here for energy, you substitute this term, which I have shown in rectangular blue color box. That is E naught plus lambda E1 plus lambda squared E2, and psi as usual, psi naught plus lambda psi 1 plus lambda squared psi 2. Since lambda is very much smaller than 1, the lambda squared is negligible. So we can ignore the higher order terms. We can take only the first two terms, that is lambda and lambda squared. So now we are going to see the first order perturbation theory. So we arrived with this expression finally. The coefficient of the successive power of lambda on both sides of this equation must be equal. That we know very well. Equating the coefficient of powers of lambda 0, that is lambda power 0 is 1. So and lambda power 1, that is lambda, we obtain. Take the case of lambda power 0, that is you take the term without lambda and equate it. Here without lambda, you will get, if you multiply this H naught and psi naught. So that's what we got it here. Similarly, in the right hand side, if you multiply E naught psi naught. So this you can very well understand that if when unperturbed Hamiltonian act on the unperturbed wave function, then you will get unperturbed eigenvalue E naught, of course, with psi naught. Similarly, now you equate the lambda lambda power 1, that is lambda. Here with the H naught, if you multiply H naught with lambda psi 1, so H naught psi 1, because naturally lambda will get cancelled because both side we are equating with lambda, and so this will become H naught psi 1. This one H naught psi 1. Similarly, if we take the other one, this lambda H prime, here you will get psi naught. So this will be equal to H naught, sorry, H prime psi naught. Similarly, on the right hand side, if we multiply E naught, with psi 1, you will get E naught psi 1, lambda term. And similarly, if you multiply lambda E1 with the psi naught, so with the psi naught, you will get E1 psi naught. So now there are two different wave functions, psi naught, psi 1, that is in different state. Now you bring same state in the same side. For example, left hand side I am bringing the term with the get psi naught. So here E1 psi naught. So this will become H naught. These two term I am bringing left hand side. That is this term and this one I am bringing to left hand side. So this will become H naught, H prime minus E1 psi naught. And the remaining thing I am bringing this to right hand side. So this will become E naught minus H naught multiplied with get psi 1. Now we got this expression, that is H prime minus E1 psi naught is equal to E naught minus H naught psi 1. Now you take a inner product with bra psi naught. So on both sides. So in the left hand side you will get psi naught H prime minus E1 psi naught. In the right hand side you will get psi naught E naught minus H naught psi 1. According to orthonormal property, you are taking inner product psi naught with psi 1. So naturally this will get cancelled. This will become 0. So right hand side will become 0. And the left hand side, you can separate this into two parts. That is psi naught H prime psi naught minus psi naught E1 psi naught. Since E naught is a number, you can take this outside of the inner product. So this will become uh, E1 psi naught inner product psi naught with psi naught. So you know very well that according to orthonormal property, this will be 1. Psi naught inner product of psi naught with the psi naught is equal to 1. So you will get finally you will get this E1. If you bring this right hand side, you will get psi naught H prime psi naught. This is the fundamental result of the first order perturbation theory. It is very interesting to note that the first order energy correction is nothing but, if you can see the right hand side, it is expectation value. By definition, it is the expectation value of perturbed Hamiltonian in the unperturbed state. Psi naught is the unperturbed state. So this is one of the interesting thing. That is, energy correction is equal to the expectation value of the perturbed Hamiltonian in the unperturbed state. That is very important. Our next task is to find the expansion coefficient of first order perturbation. Uh, we know very well that the square of the expansion coefficient gives the probability of the finding the particle. So in that way, the expansion coefficient is a very important parameter. Uh, psi naught is unperturbed eigenfunction. Hence, we can put psi naught is equal to um. Is a wave function, initial wave function, and E naught is equal to Em. This is the initial energy eigenvalue. And we have seen that H naught minus E naught into psi 1 is equal to E1 minus H prime psi naught. Now we know we can write psi 1 as a expansion of a n of 1. Here 1 represents first order perturbation coefficient due to first order perturbation into un. So we can write this in terms of expansion, that is summation over n a n of 1 un, and substitute this in the above expression. See, I have shown in the red color font, psi 1 can be replaced by summation over n, an of 1 un. And this term I am keeping as it is, h naught minus e naught, which is equal to e1 minus h prime um. Uh, Here, one simple concept is if H naught act on UN, that is wave function UN, it gives, this is unperturbed Hamiltonian. So it gives a energy eigenvalue of En. So I have replaced H naught as En. Already we have seen E naught, that is initial energy eigenfunction is Em. So this will be UN. Remaining thing I am keeping as it is. Now we are arrived with this expression, that is summation over n, an of 1 en minus em into un, which is equal to u1 minus h prime um. Now you take an inner product with the uk. In Dirac notation, uk can be written as a bra k and un can be written as a get n. Since the an1 and en minus em are the numbers you can take out. So if it is operator, you are not supposed to take out. Since it's a number, you can take out of the inner product. Uh, and right hand side, you have K, bra K, E1. I have separated this E1 M minus K H prime M. Since E1 is a number, we can take this E1 outside, and then the inner product of K with M will be equal to 0. So this term will get cancelled. So in the right hand side, you will get only the term left is minus pra k h prime get m. Now you come to the left hand side. Uh, this will be the summation has only one non-zero value. That is when n is equal to k, it has non-zero. This is 1. For all other value, it is 0. So naturally, the summation will get removed, and you will have only one non-zero term. That is when n is equal to k. So I have replaced an as ak1 and en as ek minus em, which is equal to this one minus k h prime m. Now I am interchanging this term em into ek, so naturally one minus will come outside. This minus and this minus will get cancelled. Now the expansion coefficient is, if you bring this to the right hand side, you will get k h prime m over em minus ek. This is the expansion coefficient for the first order perturbation. Here it should be remembered that k is not equal to m. K is not equal to m. That's why this first term will become 0. Because EM is the initial energy state, K is the final energy state. Due to perturbation, it may not be the same. So, we have obtained the expansion coefficient for first order perturbation. In the next lecture, we will see about the second order perturbation theory, and also we can say see the example, some example for this first order perturbation theory and the second order perturbation theory. Thank you very much for watching my video and supporting me continuously.